In this video, we're going to explore how to interpret the mixed partial second derivative, and we're also going to look at contour diagrams and see if we can infer information about second derivatives from those diagrams. But we're going to start with this mixed partial. The key observation is that this mixed partial derivative, being a second derivative, can be thought of this way. We're going to take the x derivative next, or second, and take the y derivative first, and we're going to add an interpretation on this interior calculation here, which is the y slope, or the y direction slope. If we've already computed that, then the answer to what does a derivative mean is always this kind of statement. For a small step in the, let's be clear here, positive x direction, that's what this represents. What is the rate of change of this thing here? Well, here it's not just f, it's the y slopes of that surface. Now that's pretty abstract. Let's take a look at a function and work our way through it. Our function is simply x times y, and if we slice through that graph by picking an x value, so we're going to pick x equals to k, and if we do that, we're going to get a function just of y, which is, well, k times y. It's not a dramatic shift, but it changes how we think about this. Now, what does that look like? Well, that's going to be a line. It's linear, and it's going to be a line with slope k. All right. Well, what we have here is zero intercept as well. If we dial up our x, we're going to get steeper and steeper lines in the y direction. Well, all right, let's see how that plays out next. What happens to the slope of this intersection as we change k? Well, keep in mind here, x is the same as k, so we're going to be talking about what happens as we are changing x and what happens to the y slope. So what we have here, the y slope direction, or the slope in the y direction, is equal to literally k. Because our f of y was equal to ky, take that derivative, we just get k. So if we imagine a little side view of this, with x coming out towards you, hard to draw here, but what we have is y and z, and x literally coming off the screen in your direction. If we compare any single value here, this could be, say, k equals a half, and then let's go to k equals 1, and then we'll go to k equals 2. All of these also correspond to x points. X equals a half, x equals 1, x equals 2. And so what we're seeing is, as x increases, as we take a step in positive x, what is happening to the y slopes? That's the noun that we're acting on. The y slopes are going from a half to 1 to 2. They are increasing as well. And all we know about derivatives is if the input's increasing and the output increases as well, then the partial derivative that we're talking about is positive. What we have is, as x gets bigger, the y slope gets bigger. Well, that's this mixed partial derivative here, capturing, if we increase x, what happens to the y slopes. So it is a bit of a burden. It's a more complicated statement than it felt like when we talked about concavity, though honestly that's just because we've internalized what concavity looks like and means. There's no easy graphical interpretation of this partial derivative, unfortunately, at least not one that we found that is easily expressed. It ends up boiling down to this kind of sentence. For a small step in the x direction, what happens to the y slope? Or for a small step in the positive y direction, what happens to the x slope, which would be equivalent and equal given what we've seen earlier. All right, let's do a little bit of practice with this, looking at contour diagrams. We'll start off with examples we've seen already, imagining this contour diagram and finding the following first derivative signs. So positive x is to the right, positive y is up in this contour diagram, as usual. Ask yourself for a moment, what would the sign of the x slope and the y slope be on this diagram? Pause the video for a moment, and then we'll check in. All right, the process for these is always the same. If we're taking a look at the x slope or an x derivative, we increase x by a little bit, take a step to the right, and ask what happens to the thing that we're differentiating. Well, f would be going from 1 to 2 to 3 to higher contour levels. F is increasing, and that relationships mean we have a positive x derivative. If we do increasing in y, we're at height 1, we're going to height 0, going to height -1. An increase in y leads to f decreasing, and so that corresponds to a negative slope. That's it. Takes a bit of practice, but keep your eye on the contour diagrams and ask yourself literally what happens if we take a small step in positive x, blue line, or for the y derivative, take a small step in positive y, the red line here. Next, we're going to explore how we can look at second derivatives and identify their sign from a contour diagram. We'll work through these together. If we're looking at the x partial derivative, second partial derivative, then what we are definitely looking at is, in principle, an increase in x, and looking at what that does to the x slopes. And that's a helpful way to think about it, but it's also easy to visualize this as everything in the x direction is what we care about for the moment. And if we're doing that, then what we can think about is the x height relationship. At the point P, we're at height 1, so here's P, we're at height 1, and what happens as we move along this pathway? Well, we're going to go up to the right, and the question is, does it get steeper or less steep? Well, we can see that as x increases, the x slopes, let me go back here and do it all in red. Well, we can see that as x increases, the x slopes get steeper. Okay, and also the x slopes are positive. We saw that earlier. It's actually these two facts together that are going to give us our answer. 1, the x slopes are positive. 2, as x increases, those x slopes get steeper. We can draw that. What that looks like is x slopes are positive, and because the contours get closer and closer together as we walk along this path, we're going to get steeper and steeper and steeper. Well, that looks like concave up. Concave up corresponds to a positive second derivative. You can also look at it numerically if it helps. If you are taking a step in positive x, the value of the slope as we go to the right is going up, and so if we increase x, the fx values also increase, and so we get a positive derivative interpretation as well. You may need to play that back, or you can take a look at the next example, which is the y direction, to see if you can reinforce the ideas. We're going to study again how the function changes for an increase, though this time in y, and look for what can we say about the y slopes. That's how we get two y derivatives involved. So we'll do that step here. What we have is we're at height 1 and we're going down, so we have negative slopes for y. So the y slopes are negative. All right. As we go this direction, we go from 1 to 0 to -1. The second component is that the y slopes, as y increases, the y slopes get less steep or more steep. Well, as we move out here, the contours get further apart. And so we get contours, or sorry, we get slopes that are less steep. Okay. Well, if that's the case, we can actually draw that picture now with y versus z and pick our point P. Whatever height we're at, we have negative slopes, but they're getting less steep as y increases. So we have slopes that are getting less steep. Oh, that is also concave up. It's a different shape in some sense. It's a negative slopes getting less steep rather than positive slopes getting more steep. But if you draw it, this is the key ingredient, if you draw this combination of negative slopes getting less steep, you can immediately read out the concavity. And if that is the case, we have concave up, that second derivative will also be positive. If you want to, you can also reassure yourself that as we increase y, the slopes in the y direction are increasing. We might have slopes of -1, then -0.5, then -0.05. We have slopes that are going up in numerical value, and that translates to a positive derivative. Last, and most challenging for most students, at least initially, is determining the sign of the mixed second derivative. What we're going to consider here is both ways to think about it and see if they match each other as they should. We're going to increase x, and then we're going to look at the y slopes and ask what they do. So it's going to be the same kind of logic as the last example. So let's imagine the y slopes first. We're going to focus on that. Well, the y slopes are negative. We'll put this over here. The y slopes are negative. And what happens to them as we increase x? Well, if I draw this line, I can see the function is more steep as we take that step, or more steep as x increases. Okay, this combination and this negative sign on the slopes gives us what we need. Here's how we connect the dots logically. We have negative slopes, and you can imagine this as negative slopes drawn out if you like, and they are getting more steep as we increase. Now it's not strictly one plane, but all the logic about concavity works out the same way. This looks concave down. If you want to think about the values of the slopes, we'll draw this a bit more dramatically here. The slopes would go from, say, -1 to -2 to -3. Oh, the y slopes are more steep. That package together means the y slopes are decreasing in number. The values here are strictly just going down, and so we are going to have a negative derivative. The thing that we increase x results in a decrease in what we're tracking, which is the y slopes. That's what a negative derivative corresponds to. Notice that we can do exactly the same logic applying with x slopes. So we could talk about increasing y and looking at the x slopes. Our first fact is that the x slopes are positive. As we take As we take steps in positive x, we go from height 1 to height 2 to height 3, and we're going up. So the x slopes are positive. If we then take a step in y and ask the same question, we can see that as we do that, the contour lines are getting further apart. So the x slopes are less steep as y increases. And if that's the case, we can draw that scenario. So we would have y slopes that are doing their thing, and then they're getting less steep. Well, that would be numerical values like a slope of 2, going down to a slope of 1, going down to a slope of 0.5. These numbers are decreasing, and so the y slopes are decreasing. So for the same rationale, we increase y, sorry, those are x slopes. As we increase y, the x slopes go down. What kind of derivative is that? It's a negative derivative. If it helps, sketch this out as if it was a single variable problem. It gives you the right logic every time, but keep in mind what you're mixing is two variables together. There's no question about that. We're talking about increases in x and asking what happens to the y slopes. So we're going this way and that way somehow at the same time, or mixing and matching, we're going this way and that way at the same time. So the interpretation is still more challenging, but if we just want to find the sign, these kinds of diagrams are extremely helpful and effective.